Okay, so the local recording should be going, except that it keeps resetting the side. What is going on? What? Okay. So we already have our first technical hiccup. I think WebEx keeps resetting my camera settings, which is not okay. Let me just get this fixed. Okay. All right. So let's begin. Okay, so what I want to talk about today, this was supposed to be sort of before motion planning. So before we did motion planning, we mostly focused on algorithms for doing different things in the plane, building convex hulls or Voronoi diagrams or Delaunay triangulations and so on. But a lot of these things exist in higher dimensions just as well. The problems themselves usually generalize pretty naturally to the higher dimensions, but the algorithms are often much more difficult. Sometimes, though, the algorithms are also just as easy. So we did linear programming earlier in the plane when I was talking on the board. And for linear programming, if you want to go to higher dimensions, you pretty much do exactly the same thing. You repeatedly add a new hyperplane to see if you're still a new half space constraint to see if your current optimal vertex is still feasible. If the vertex isn't feasible, then you need to move it on to the bounding hyperplane of the new constraint, and you solve a linear programming problem one dimension lower on the new bounding hyperplane. But for other problems, the problem itself generalizes nicely, but the algorithms don't generalize so well. So for example, if I wanted to generalize like convex hulls to higher dimensions, it's actually exactly the same definition before. It would be the intersection of all the half spaces containing all the input points. Upper and lower envelopes also generalize pretty naturally. So in the plane, we would have a bunch of lines. And for upper envelope, we'd ask, what is the intersection of the half spaces going above the lines? Well, in higher dimensions, you get the intersection of half spaces above a bunch of hyperplanes. The ones that are a little bit weirder that we've seen before, Voronoi diagrams and Delaunay triangulations. So Voronoi diagrams, I guess, would be pretty natural. In the plane, each cell of the Voronoi diagram was the set of points for which a site is the closest to the points. But now in higher dimensions, pretty much the same definition works. You have these sites, you have a bunch of cells that describe which the set of points for which the site is the closest. Now, instead of the cells being convex polygons, they're instead just going to be convex polytopes in general. Delaunay triangulations are a bit weirder. So if you could do a higher dimensional Delaunay triangulation, instead of a triangulation, you now have a higher dimensional tetrahedra. So let's say in d dimensions. In d-dimensional space, you'd have a tetrahedra defined on d+1 points. And before we said that when you have a triangle, the circum triangle around each triangle shouldn't contain any other points for the Delaunay triangulation in the plane. Now, if you look at the circumhyperspheres of these tetrahedra, they shouldn't contain any other points. And now probably be a great time to ask, can everyone see the words I'm writing? Oh no, you're not able to read it? It's very blurry. Okay. Sort of blurry. Trying to think if there's a good quick fix. I'll try writing bigger. I'm afraid to move my desk at the moment. I'll try to write bigger. The local recording is in 1080p. Hopefully that's going to be clear enough. I don't know what WebEx is doing. I can only move the camera so close with my desk set up the way it is. But I'll try to write bigger for the rest of the lecture. Okay. So all these problems, they generalize, the problem itself generalizes fairly naturally. The algorithms don't. So for example, if I want to compute convex hulls in 3 dimensions, the best way, according to the textbook at least, is to use a randomized incremental construction. That's quite a bit more complicated than the gram scan or the Jarvis march that we saw at the beginning of the semester. And this implies intuitively that as you go up into higher dimensions, solving these problems becomes increasingly difficult. But one interesting thing that I wanted to talk about today is that sometimes the more difficult problems that we want to solve in lower dimensions, like Delaunay triangulations or Voronoi diagrams, they're actually the same, or at least they can be reduced to solving some of the easier problems in higher dimensions. So I'm going to show you today that if I want to find a Delaunay triangulation in the plane, then this is going to be equivalent to finding the boundary of the convex hull of a 3D point set. And if I want to find the Voronoi diagram of some sites in the plane, this is equivalent to finding the boundary of the intersection of a bunch of 3D half spaces. And you actually do a direct reduction from the planar problem up to the problem in higher dimensions. This will probably be our main example of looking at higher dimensions when the algorithm isn't just completely obvious what to do. If you're interested in algorithms specifically for higher dimensions, you can look at that book chapter I mentioned for Voronoi diagram, or sorry, for computing the convex hull of points in 3D. Okay. Okay, so both the examples I'm going to talk about, they're going to involve this 3D paraboloid. So is that any better? That writing? Okay, so we're going to consider this paraboloid z equals x squared plus y squared. And what we're going to do is we're going to look at points in the plane. So generally a paraboloid is going to look something like this. And here is the plane below it. And what we're going to do is we're going to look at points lying in the plane, and I'm going to define something called a projection, or a lift that takes these points in the plane and lifts them up to lie on the paraboloid. So let's say I have a bunch of points down in the plane. These could be the vertices for a Delaunay triangulation or the sites for a Voronoi diagram. We're going to have these things called vertical projections. Sometimes I might call them lifts. And we take a point P at location P comma X comma PY, and it goes to what I'll write as P up arrow, which is also a PX comma PY, but its Z coordinate is going to be PX squared plus PY squared. So you can imagine shooting some rays straight up onto the paraboloid, and you get the lifts of these points down in the plane. This map is a bijection, so it's a one-to-one mapping between the points down here and the points up there, and vice versa, invertible and so on. So yeah, so it's well defined, like how I'm going to lift all the points. And sometimes if I'm given a big set of points, capital P, I may talk about the lift of the entire set simultaneously, and I'll use capital P up arrow, similar to what we've been doing the rest of the semester. Okay. So what we're going to do is we're going to take these points down here in the plane, we're going to lift them up to the paraboloid, and we're going to start talking about the convex hull of these points up in the paraboloid. In particular, we're going to focus on the lower convex hull, which is defined like in the plane. It's the intersection of all of the upper half spaces that define, that contain these points up on the paraboloid. Okay. So, assuming that the points are in general position to start with, each face of the lower convex hull of P up arrow happens to be a triangle. This is sort of like how, assuming general position, each face of the convex hull in 2D is a line segment. So if I take the convex hull of all these things, I might get a bunch of different triangles as follows. So here is it becomes really hard to draw things in 3D. So here's a better picture, which may be kind of blurry because I turned the focus off. But hopefully the idea makes sense. I have all the points down in 2D, and I lift them up onto the paraboloid. The lower convex hull of the points on the paraboloid, it's a bunch of triangles where if I look at everything above the triangles, I see every single point lies above all those triangles. But now the neat thing about these particular triangles is if you project the line segments forming the boundary of the triangles back down into the plane, then you actually end up with a triangulation of the plane. And it's not just any triangulation, it actually ends up being the Delaunay triangulation. So in particular, if I have 3 points from my original point set, so a triangle, or sorry, so PQR in the original point set is a triangle if and only if P up, Q up, R up is a face of the whole. So does the statement that I'm making make sense? Okay, I don't hear. Okay, I see one person typing. Thank you, Connor. Okay, so let's see how we're going to prove this. To prove this, we need to remember what's true about the triangles of the Delaunay triangulation and also what's true about the triangles of the convex hull. So we have this thing called the Delaunay condition, which stated that PQ and R form a Delaunay triangle if and only if there's no other point in their circumcircle. Oh, and I should have mentioned this earlier. If you are having trouble seeing because of connection quality, or I just don't have a camera set up well, I am following the notes that are available online. It may be helpful for you just to follow along with those notes. Okay, so PCAR is a triangle if and only if the circumcircle through PQR is empty. So that's what's true of Delaunay triangulations. We also need to worry about what's true about this the lower convex hull. And at the beginning of the semester, I said there's going to be for the plane, a line segment lies in the convex hull if and only if all the points lie to one side of the line through that line segment. And it's a similar statement here. A triangle lies on the lower hull if and only if every other point lies above the plane going through the triangle. So in order to prove this statement that the triangles in the convex hull correspond to the triangles in the Delaunay triangulation, what we're going to do is say, I'm going to prove the following lemma. Probably don't need this statement now. That if I have 4 points, P, Q, R, and S, point S is going to lie in the circle through P, Q, and R. if and only if the projection of S lies above the plane going through the projections of P, Q, and R. Okay. Any questions on why we want to prove this lemma? Okay. So how are we going to show this? To show this, I'm going to establish some facts about points and planes that pass through this paraboloid. And then we'll use those facts in order to get to the proof of the lemma. Okay, so what we're going to do is we're going to consider some arbitrary but not vertical plane in 3D that lies tangent to the paraboloid and ask, well, what's going on with that plane? So fix a plane lying tangent to paraboloid. I'm not sure I ever gave this paraboloid a name. In my notes, I'm calling it psi. So take a plane that lies tangent to the paraboloid at point a comma b comma a squared plus b squared. Okay. Every point on the parabola has this form, maybe a squared plus b squared. Okay. So what we're going to do is we're going to try to figure out what's the equation for this plane so that we can know more about it. And to do that, what we're going to do is we're going to look at the partial derivatives in the a direction and the b direction for this plane. Okay, so we might observe that partial z over partial x is equal to 2x, and partial z over partial y is equal to 2y. That's just me taking the partial derivative of x squared plus y squared. At this particular tangent point, a comma b comma a squared plus b squared, that means the partial derivatives evaluate to 2a and 2b. Okay. And then that means the plane has to have the form z equal to 2ax plus 2by plus some value gamma where we don't know what gamma is yet. So let me draw what's going on here using another color. So we have a paraboloid, and I'm interested in understanding a plane that intersects the paraboloid at this position a comma b comma a squared plus b squared. the partial derivative at that point on the paraboloid, and therefore also on the plane itself, must evaluate to 2a in the x direction and 2b in the y direction. And so the equation for the plane is z equals 2ax plus 2by plus some value gamma. We don't know what that is, but it's going to lift the plane up or down. My son is nearby, you hear him. Okay, so we're going to solve for gamma now by looking at the tangent point. Okay, so at the tangent point, we know z is equal to a squared plus b squared. And this must equal 2ax plus 2by plus gamma. Okay, and if we do the algebra, then that implies gamma is actually equal to negative a squared plus b squared. Oh, sorry. Z is equal to a squared plus b squared at the tangent point. X is equal to a at the tangent point, and y is equal to b at the tangent point. Now we can solve for gamma, and we see that gamma is equal to negative a squared plus b squared. And so the tangent plane must be z equals a squared plus b squared minus, z equals 2ax plus 2by minus a squared plus b squared. Okay. So here's the equation of this plane going through the tangent point. It'll become clear in a second, hopefully, why I am doing all this. Now, if you imagine we lift the plane up lambda units, lambda squared units. If we lift up the whole plane lambda squared units, it's going to cut through the paraboloid instead of lying tangent to it, and we'll get a new equation. Z equals 2ax plus 2by minus a squared plus b squared plus lambda squared. Very hard to draw this figure. Say the tangent plane. Okay, so imagine we lifted it lambda up. Now what's going to happen, if you lift it up lambda units, it's going to cut through the paraboloid at certain positions. We're going to finish this by discussing where does the lifted plane intersect the paraboloid. So the lifted plane intersects psi at certain positions. Specifically, we have to have x squared plus y squared, which is the z-coordinate of the paraboloid, equal to 2ax plus 2by minus a squared plus b squared plus lambda squared. You solve for this, and you end up getting x minus a squared plus y minus b squared is equal to lambda squared. So the x and y coordinates, where this hyperplane that used to be tangent, but I lifted it up lambda squared units, the x and y coordinates must be such that x minus a squared plus y minus b squared is equal to lambda squared. Does this equation look familiar? Right. What we ended up with is the equation for a circle of radius lambda with center at a comma b. In this process, I started with a completely arbitrary plane that was tangent to the paraboloid, and I lifted it up an arbitrary amount. So this risen up plane we're talking about could have been any plane whatsoever, as long as it's not vertical. So no matter what plane you have, the intersection of that plane with the paraboloid, assuming it intersects at all, is going to give you the equation for a circle if you project it back down into normal r squared, the place where the original point set lives. Okay, so with this knowledge now, we're pretty much ready to prove that lemma that if I have the 4 points P, Q, R, and S lies within the circle through P, Q, and R, if and only if S lies above the plane passing through lifted P, Q, and R. Okay. So take P, Q, and R. Then what we see is the projection of their circumcircle. So phi is actually the intersection of some plane through P up, Q up, and R up with the paraboloid. Okay. Now is when I wish I had a bigger board. I think I may have told you the lemma backwards. Okay, yeah. All right, so take a point S. If S is outside the circle, then S up Okay, let's just start drawing. So my 3 points, P, Q, and R. And we have the circle going through them. Now if I lift up to the paraboloid, here's P up, Q up, and R up. There's a plane passing through P up, Q up, and R up, and the intersection of that plane with the paraboloid itself forms a circle on the paraboloid. And there's a plane going through this intersection. And now if I have a point S that lies outside the circle through P, Q, and R, that means S has to lie elsewhere on the paraboloid. In particular, it has to lie above the plane passing through P up, Q up, and R up. And if S were to lie inside the circle, it would have to lie below that plane, because everything on the inside of this lifted circle is below the plane going through the circle, and everything on the outside of the lifted circle is above the plane through the circle. So if S is inside the circle, then S up lies below plane through P up, Q up, and R up. Okay. Otherwise, it's got to lie on the part above the plane. And then this implies that there can't be a triangle through P up, Q up, and R up on the convex hull if S up lies below it. Okay. And then vice versa, if S was outside the circle, S up would lie above the plane through P up, Q up, and R up, which would be fine. It wouldn't violate there being, at least S alone wouldn't violate there being a triangle through P up, Q up, and R up. And therefore, there's going to be empty circumcircles through the points of the plane, if and only if there are no points in the lift that lie below the plane or the triangle through the 3 lifted points. The triangles of the Delaunay triangulation correspond to triangles in the convex hull of the lift of the points. And I think I miswrote earlier when I said that lemma. The circle is empty. S is inside the circle if and only if S up lies below the plane through the 3 points. Okay. Any questions about how this lift worked? Mm-hmm. Yes, yes. Right. So the goal earlier was let's consider any plane whatsoever. To form that plane, we'll start with a plane that's tangent to the paraboloid. We'll learn about its exact equation on the paraboloid, and then we'll lift it up lambda units to get to the plane that we really care about. And then, look, the intersection of this arbitrary plane with the paraboloid, it projects down to a circle in the plane. The intersection of the plane through P up, Q up, and R up projects down to the circle through P, Q, and R. S is going to be on the inside of the circle if and only if S up lies on the part of the paraboloid kind of interior to this intersection, which means S would have to lie below that plane. And then because of the Delaunay condition, triangles only when there's empty circles, and because of the convex hull condition, triangles only when there's no other point below you. We see that the projected the triangles for the Delaunay triangulation, they lift up to exactly the triangles of the lower convex hull. Okay. So there's one nice application of this result. When you're building the Delaunay triangulation of points in the plane, you need a way to know whether or not a point S is inside the circumcircle for three other points P, Q, and R. So what we can do is we're going to define a function in circle P, Q, R, S, and it's going to be negative if S outside the circle, 0 if S on circle, and positive otherwise. Well, we know S is outside the circle if and only its projection lies above the plane going through the lifts of P, Q, and R. Okay. And so you can actually compute this by computing a determinant. So in circle, P, Q, S, R, and S can be defined as the determinant of Px, Py, P squared x plus Py squared, 1 Qx, Qy, q squared x plus qy squared 1, rx, ry, r squared x plus r squared y 1, sx, sy, s squared x plus sy squared 1. This determinant tells you, the sign of this determinant is going to tell you whether or not this point s up lies above or below the plane going through p up, q up, and r up. And so taking this determinant is also the same as deciding whether s is inside or outside the circle through p, q, and r. And when you're building the Delaunay triangulation, even in the plane, you'll want to do this determinant a lot in order to run your Delaunay triangulation algorithm. Okay. So that is Delaunay triangulation being the same as the lower convex holo points. Does anyone else have any questions on that subject before I move on to Voronoi diagrams and upper envelopes? All right. So Voronoi diagrams and upper envelopes actually goes a bit quicker because now we already know a lot about what this paraboloid looks like and what planes through the paraboloid look like. Okay. So I want to start by saying, like earlier in the semester when we first talked about point line duality, I showed you that the lower convex hull is point line dual to upper envelope. And then later in the semester, I showed you the Delaunay triangulation is planar dual to Voronoi diagrams. Now, I probably could prove what I'm about to show you by taking a bunch of duals and just doing a bunch of algebra, but intuitively, it kind of makes sense what I'm about to show you. The dual of the Delaunay triangulation is the Voronoi diagram. The dual of the convex hull is the upper envelope. So Voronoi diagrams, it turns out, lift up to upper envelopes. I just think that's, I mean, the algebra probably suggests this should be the case, but I think it's a nice bit of serendipity that this works. Okay, so let's talk about what we're going to take the upper envelope of. So for convex hulls and Delaunay triangulations, I lifted all of the points in the plane up to points on the paraboloid. Now what I'm going to do instead is I'm going to take points in the plane and I'm going to lift them up to planes that lie tangent to the paraboloid. Okay, so if you're given a point P equals AB in your input point set, we're going to define H of P as this plane that lies tangent to the paraboloid at A comma B, which was Z equals 2AX plus 2BY minus A squared plus B squared. And that lies tangent to phi. Okay. That's going to be H of P. Now take any point Q equal to Q sub X comma Q sub Y. From earlier, we defined Q up to be q sub x, q sub y, q sub x squared plus qy squared. The hyperplane h of p lies tangent to phi. And so it actually lies below every single point, tangent to psi. So it lies below every single point on that paraboloid psi. In particular, it has to lie below q up. We can compute or talk about the actual vertical distance from q up down to the plane h of p. So by definition, this would be q of z minus 2a qx plus 2b qy minus a squared plus b squared. Let me see how much I can simplify. Well, maybe just trust me. You do a bunch of simplifications, you complete some squares, and this ends up solving to q sub x minus a, quantity squared, plus q sub y minus b, quantity squared. This expression here is the square of the distance from q to p. Okay. So what this means is the further down, the further p is from q, the further down the hyperplane h of p is when you're going straight down from q. And in particular, if we define capital H of P to be the set of all of these hyperplanes for our set of sites, and we take any point Q in the plane, if we look at Q lift and we take a ray and project it straight down, it's going to run into these hyperplanes in increasing order of distance that the sites are from Q. If you want to visualize that, let's pretend that we are doing Voronoi diagrams in one dimension, lifting up to a paraboloid in 2 dimensions. So here's our paraboloid psi. And here's our plane. And we have a collection of sites, P1, P2, P3. I'll call that one P3 and this one's P4. Now, if we look at the move P1 a bit closer too, so I can actually draw this. Okay. If you take these these lines lying tangent to psi above each of these positions, like here is h of P1, h of P2, h of P3, h of P4. And now I take any other point Q. So Q is right here. And I look at where Q lies in the parabola. As I work my way down, I'm going to hit h of P2 first, and then I'm going to hit h of P3, and then I'm going to hit h of P1, and then eventually I'll hit h of P4. 2 is the closest site, P3 is the next closest site, P1 is the third closest site, P4 is the fourth closest site. So I'm running into them in increasing distance order from Q. And so if U of P is the upper envelope of all those of capital H of P, if I look at the boundary of the upper envelope, it's going to be the positions where 2 of these planes are both the closest going straight down from some common point. And therefore, they project to locations where 2 of the sites are equally close to a common point. The boundary of the complex must project down to be exactly the Voronoi diagram for all the sites in P. Any questions on Voronoi diagrams and upper envelopes? Okay. I feel like I must be going faster than normal because we have another 15 minutes left and I have one short thing to talk about. I think it's because there's not as many questions. Then again, there's fewer reviews, so maybe that should be expected. Oh, yes. And then I had this picture earlier of the Delaunay triangulation lifting up to be the lower convex hull. Here's a similar picture that I can't hope to draw, where you have all the sites and they form a Voronoi diagram, and they lift up to be the upper envelope of all of these hyperplanes that are tangent to the paraboloid. And if you look at the intersection of all of these hyperplanes lying on the upper envelope, those intersections project down to be the Voronoi diagram itself. Okay. All right, so that leads to the last thing I want to talk about. So far, a couple weeks ago, we discussed Voronoi diagrams. I said the cells tell you which point, the cells are defined by the site being the closest site for all the points within the cell. You can actually define what are called higher order Voronoi diagrams, where you change the definition slightly. Okay. So there's something called the order K Voronoi diagram. And the way the order K Voronoi diagram works is you subdivide the plane up into cells, but each cell is based on the K closest points to each site. Or sorry, each cell is based on the K closest sites to each point. So for example, order 2 Voronoi diagrams, you could take every cell and you could label them with which pair of sites are the closest to the points within the cell. In order 3 Voronoi diagram, you could label every cell with the 3 sites that are closest to the point. Okay. This works very nicely with that lemma I showed you earlier, where if I take a point Q and I lift it up to the paraboloid, and then I look at all of those hyperplanes intersected by the ray going down from Q up, that can actually tell us all about these different cells in order K Voronoi diagram. So we had capital H of P, which was the collection of all those tangent hyperplanes made from, you take one of the sites, you look at tangent planes. You take a site, you look at the plane tangent to the paraboloid going through the lift of the site. Well, all of these planes, they form an arrangement in 3 dimensions consisting of triangles and edges and vertices. And also, I guess, tetrahedra. It divides up 3-dimensional space into these polytopes, faces, edges, and vertices. When we were talking about arrangements and we were doing half-plane discrepancy, I talked about these things called levels, where the kth level of the arrangement it's the set of points in 3D, or at least in this case, it's a set of points in 3D, such that there are at most k minus 1 hyperplanes above the points and n minus k hyperplanes below. They're just planes. Okay. If I take a point Q from the plane and I look at its lift into the paraboloid, then I shoot a ray straight down from the lift. I'm going to pass through all of these planes in increasing distance order that Q is from the respective sites. Okay. If I go K planes down, then I learn which cell of the K order Voronoi diagram that Q belongs to. So the bottom boundary of the Kth level of this arrangement actually projects down to the boundary of the order K Voronoi diagram. And then one final neat fact. The book talks in particular about a special kind of order K Voronoi diagram called the farthest point Voronoi diagram. Here you have the plane divided up into cells. Each cell tells you which site is the farthest from the points in the cell. Well, if I take a point Q and I look at its lift and I want to know the farthest site, then I would shoot a ray straight down and I'd look at the last hyperplane I intersect. Which means the farthest point Voronoi diagram is actually a projection of the lower envelope for all these tangent planes. And yes, I can give you a figure. Let's see. So I'm going to do a figure for the K-order Voronoi diagram figure. Or sorry, a figure for the K-order Voronoi diagram theorem. So we're using blue for our parabola. And let's say I have, here's my plane. And I have these sites, P1, P2, P3, P4. And I have my tangent planes. Let's say I want to know about the, well, first, if we want to know about the Voronoi diagram, we'd look at the upper envelope. So it'd be P1 up until here, where it intersects with P2 cell, where it intersects with P3 cell, where it intersects with P4 cell. But if I want to learn about the order 2 Voronoi diagram, instead of the order 1 Voronoi diagram, which is one we normally talk about, then I'd look at the second level of the arrangement. And the second level would be all this stuff I'm filling in with orange. Yeah. So that's level 2, which implies if I want to know about the level 2 Voronoi diagram, so let me make sure I did this correctly. This is less interesting than the book's exam. That's fine. So this part of the level 2 projects down to this section, in this example on the line, which tells me sites 1 and 2 are closest. Here, sites 2 and there's the problem. Between here and here, sites 2 and 1 are closest. Between here and here, sites 2 and 3 are closest. Between here and here, we have sites 3 and it looks like 2. Between here and here, we have sites 4 and 3, or rather 3 and 4 in that order. And then we have 4 and 3 in that order. So the intersections for level 2 tell you exactly which are the 2 closest sites and in what order they are, if you project back down. Any questions on that fact? And also, I am sorry if, okay, not too much chatting going on. Any questions about higher order Voronoi diagrams? Right, so I'm doing the drawing and I'm doing the drawing where I'm doing the one-dimensional Voronoi diagram lifting to a two-dimensional arrangement. But it works in all dimensions. I mean, the algebra I was showing on the board, if I want a Voronoi diagram in 2 dimensions, I would lift up to a 3-dimensional paraboloid. Level 1, the boundary of level 1 would tell me about the Voronoi diagram. The boundary of level 2 would tell me about the order 2 Voronoi diagram. The boundary of level 3 would tell me about the level 3 Voronoi diagram. This actually works in higher dimensions as well. If I want to know the Voronoi diagram for a bunch of points in 3D, I could lift up to a 4-dimensional paraboloid to a bunch of tangent hyperplanes and look at their arrangement and their levels, and that would tell me about the different order Voronoi diagrams in 3D. The figure, though, I drew it going 1D to 2D because otherwise it just would have been a mess. Does that answer your question? Okay. So then the last thing I wanted to say was the book has a section on what's called the farthest point Voronoi diagram. The cells tell you what is the farthest site for each point in the cell. And again, if I go and I look at the tangent hyperplane for a site, or sorry, if I look at a point and I look straight down from the point, I'll pass through all these tangent planes in increasing order of distance for the plane's sites. The last plane I pass through looking straight down tells me what is the farthest site for my point. And so the farthest point Voronoi diagram is the projection of the lower envelope. Of all those tangent planes. That's not to say you would want to compute the farthest point of the Voronoi diagram by computing the envelope on the paraboloid. The envelope is much more simple than you would get if you just had arbitrary planes in 3 dimensions. But it's, I don't know, I think it's a pretty neat fact. Okay, so any other questions on the lecture? If not, I'll probably stop recording and then we can try to figure out how I should fix any technical bugs we have. Okay, so give me just a minute. I'm going to turn off the recording and I'll put on a face camera.